From the last video, I started to talk about complex geometry, and then we talked about locus of complex, locus, right, in the sense of complex numbers. So here I'll be looking at triangle geometry with complex numbers. So let's see. So one thing, something close to this would be what I have a playlist talking about coordinate geometry. So I know there'll be some intersections, except that here we are dealing with complex numbers. So triangle geometry with complex numbers. First, let's start with complex plane basics. First of all, we represent points in the plane as complex numbers. Say point A, x1, y1. Normally x1, y1 for coordinate geometry is in the real number system. Like x1, x talks about the x-axis, y talks about the y-axis. But in the case of complex planes, right? So the x1, y1 is coming from z1, which is x1, iy1, meaning that every x you see and every x you see is real, every y you see is imaginary on the Argand diagram, not on the Cartesian coordinate system like we have for the coordinate geometry case, right? So point B, which is x2, y2, is coming from z2, which is x2 plus I, y2. So, and we have key operations talking about distance. So if you have z1 and z2, okay? So if you have z1 and z2, the distance between them, AB, is absolute value of z1 minus z2. And it will be okay, it will be the same as z2 minus z1. I think I'm going to give a bonus proof, a bonus solution later to the problems at the end by showing that absolute value of z1 minus z2 is equal to absolute value of z2 minus z1. And then for z1 minus and z2 also, the midpoint is z1 plus z2 divided by 2. And then the rotation by angle theta is this. Z implies z e raised power I theta. So rotation doesn't change anything. That's basically what this is about. So rotation by angle theta implies that is the same thing as z e raised power I theta. And of course, before now we have already seen that this is a polar form, right? E raised power I theta is the same thing as cos theta plus I sine theta. All right. So there's a rotation down there. You're going to see all of that. So let's look at triangle representation. So let a triangle ABC have vertices z1, z2, and z3, right? And then we can begin to talk about concepts like collinearity. So for collinearity, for instance, 3 points are collinear if z1 minus z2 all over z1 minus z3 is real. If you after evaluating this, you get a real number, then you can say that these 3 points of a triangle are collinear. And of course, it's no longer a triangle if 3 points are collinear. You just have a straight line in that case, right? So check if z1 equals 1 plus I, Z2 equals 2 plus 2I, and Z3 equals 3 plus 3I are collinear. Of course, from this, so for the way it always already looks, you can already see that this is I plus I1, and Z2 is just 2 multiplied by I plus I1, and Z3 is 3 plus I plus I1. I mean, Z1 is 1 plus I, right? Z2 is 2 into 1 plus I. Z3 is 3 into 1 plus I. So automatically, they basically have the same 1 plus I. So they are collinear by that fact alone. But of course, if you want to follow this idea of the collinearity condition, so you can go ahead and do Z1 minus Z2 all over Z1 minus Z3. That's I 1 plus I minus 2 plus 2I. So that will be 1 minus 2 minus 1. I minus 2I, that's minus I. Then 1 minus 3, that's minus 2. Then I minus 3I, that's minus 2I. Then if you factor out 2 from here, so you have, or even minus 1. So you have minus 1 into I plus 1, then minus 2 into 2 plus, uh, or I mean, you can take out minus 1 and you then have 1 plus I over 2 plus 2I. And that's basically 1 over 2. So since the result is real, so this is a real result now. So you can see these points are collinear. So they cannot form a triangle because they are just lined up like that. They are, collinearity means that Z1, Z2, Z3, Z1, Z2, Z3 lie on the same line. Or better still, I think it's better to draw the line first. So collinearity means this is Z1, this is Z2, and this is Z3. They all lie on the same line. That's collinearity. Collinearity. Okay, so that means that's not forming a triangle like that. So if you are asked the question like, do these three form a triangle? All right. Do these three do it, like maybe you are given 3 points in the complex plane and you want to check if they form a triangle. So just check their collinearity. If they are collinear, then they cannot form a triangle. So here you have a triangle area So the area of a triangle in the complex plane is this. Area is equal to half absolute value of the imaginary part of z1 minus z2 into the conjugate of z3 minus z1. Okay. So if for instance, okay, I think I need to do this. One plus j, 4 plus 2. One j is j, so not so be sure of that. So you have 1 plus j, 4 plus 2j, 2 plus 5j. Okay. So 1 plus j, 4 plus 2j, 2 plus 5j, right? 2 plus 5j. Yeah. So imagine that z1 is 1 plus j, z2 is 4 plus 2j, and Z3 is 5 plus 2j. I have a feeling one is not correct. 2 plus 5j, yeah. 4 plus 2j, 2 plus 5j, yeah. 2 plus 5j. 2 plus 5j. I want to find the area, right? And we know area here is equal to half, right, of the absolute value of the imaginary value of the imaginary part of Z2 minus Z3. Okay, imaginary part of everything. Okay, imaginary part of, let me even do this. So imaginary part of Z2 minus Z3. Then the conjugate, the imaginary part of Z2 minus Z3, and conjugate of Z3 minus Z1. Oh, Z2 minus Z1, sorry. Z2 minus Z1. Then the conjugate of Z3 minus Z1. So the conjugate of this, let me confirm for the last time. Z2 minus Z1, then conjugate of Z3 minus Z1. All right, I think we're good now. So, um, so with this in place now, let's see. First, so it means that this area now, this area will be half into the imaginary part of, so Z2 minus Z1. So for Z2 minus Z1, right, that's 4 plus 2j minus 1 plus j. So we have that. Then into Z3. Z3 is 2 plus 5j. Z3 is 2 plus 5j minus Z1. That's 1 plus j, like this. The conjugate of that and the determinant like this. So, and then we go ahead and we have area equals 1 over 2 imaginary part of, so we can open up this. So this is 4 plus 2j minus 1 minus j. This is all this now. Then we have 2 plus 5j minus 1 minus j. All this, the conjugates. Then, okay, I close this and then absolute. So in that case now, I have the area to be 1 over 2 into the imaginary part. So try to tidy things up. 4 minus 1 is 3. 2j minus j is j, right? 2j minus j. So don't forget this. 2j minus j is j. Then here, 2 plus 5j. I mean, 2 minus 1 rather is 1. 5j minus j is 4j. That's plus 4j. 2j minus j is plus j, sorry. Yeah. 2j minus j is plus j. 5j minus j is plus 4j. 2 minus 1 is 1. 4 minus 1, 3. So the conjugate of this, okay? And then we have this. So we keep going. Area now is still equal to, so area is equal to 1 over 2, the absolute value of the imaginary. So we have 3 plus j into the conjugate of 1 plus 4j is 1 minus 4j. So by doing this, we don't need to write the conjugate at the top again because change the sign, we have the conjugate. So now we can multiply these two. So it means that the area is equal to 1 over 2 absolute value of the imaginary of, so let's do this. 3 times 1 is 3. 3 times minus 4j, that's minus 12j. J times 1 is plus j. J times minus 4j, that's minus 4j squared. All right. So the imaginary of that So 3 times 1, 3. 3 times minus 4, that's minus 12j. J times 1 is j. J times minus j, that's minus 4j squared. So that means the area now, area is equal to 1 over 2, absolute value of the imaginary part of 3 minus 12j. Okay, we can already tidy this up, so we can take that out of the minus 12j plus j, that's minus 11j. Then for this, we have minus 4. J squared is minus 1. All right, we've done all this in previous videos. So area then keeps going. Area is now 1 over 2 into imaginary. Okay, 1 over 2 into the imaginary part of 3 minus 11j minus and minus plus, that's 4 absolute. So area, so that area now is equal to 1 over 2 imaginary part of 3 plus 4 is 7 minus 11j. So now we have area now to be equal to 1 over 2 imaginary part of 7 and so absolute value, the imaginary part of 7 and minus 11j is minus 11. So this imaginary part, so but this operation gives minus 11. The imaginary part of 7 minus 11j is minus 11. So that means the area then, the area is equal to 1 over 2 times 11. So that means we have 11 over 2 square units. 11 over 2 square units. Or if you like, that's 5.5 square units. Like that. And that's why for this Python code gives us that result. So you have Z1 is 1 plus J, 1J, Z2 is 4 plus 2J, Z3 is 2 plus 2, 5J. And then the area is absolute value of, so this is now coded into it. So Z2 minus Z1 multiplied by Z2 minus Z3 conjugates. So you extract the imaginary part of the conjugate of that, and then you get, so for all of that, and you divide by 2, that's 5.5, which exactly we got right here also. Okay, so then we talk about the centroid. So talking about the centroid G is Z1 plus Z2 plus Z3 divided by 3. So the midpoint is when you add everything and you divide by 2, right? Did you talk about midpoint previously? Yeah, okay, midpoint for 2, right? So the centroid is Z1 plus Z2 plus Z3 divided by 3. So if you let Z1 to be I plus J, Z2 is 4 plus 2J, the same one, Z3 is 2 plus 5J, then it means you have Z1 plus Z2 plus Z3. That's 1 plus J plus 4 plus 2J plus 2 plus 5J. So we can add 1 plus 4 plus 2, that's 7. J plus 2J, 3J plus 3, 8, 5J, that's 8J, all divided by 3. So if you split it into real and imaginary, that's 7 over 3 plus 8 over 3J. So the real part is 7 over 3, the imaginary part is 8 over 3. 7 over 3 is 7 over 3 is the same thing as 2, 1 over 3. That's 2.3333. 8 over 3 is 2 over 3. That is 2.666667. So, and that's exactly what we get when we run all this here. So here, of course, we impute the vertices. Then if we run this now, this is 2.333, which is 7 over 3, and this is 2.6667, which is 8 over 3. So if you calculate it, to calculate the centroid, you have G is Z1 plus Z2 plus Z3 divided by 3, and then you print that, you get your result. Okay, then we have the circumcenter. The circumcenter, the circumcenter O satisfies that the absolute value of Z minus Z1 is equal to absolute value of Z minus Z3 is equal to absolute value of Z minus Z3. That's like the point equidistant from every part. So a useful identity here would be that Z minus Z1 is all over absolute value of Z minus Z1 is equal to Z minus Z2 all over absolute value of Z minus Z2. That's a very useful identity in this case for circumcenter. So, and then we have, if you do all that, you take the conjugate minus Z1 conjugate. So what we are doing here is to use this identity now. So if you take A to be Z2 conjugate, minus Z1 conjugate, then you take B to be Z2 minus Z1. So it means you can switch it anyhow you like it. So if B is Z2 minus Z1, and then A is Z2 conjugate minus Z1 conjugate, then C can then be absolute value of Z2 squared. Uh, you take the absolute value of Z1, you square it, minus absolute value of Z1, you square it also. Then D3, you have Z3 minus Z2 for E, and D is for the conjugates. then f can then be absolute value of z3 squared minus all of that. Then you can have the denominator to be like this, a times e, right? A times e, minus d times b, following all that, and you get the circumcenter to be 2.0454, blah, 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 all of that. Continue like that. Okay, so so we have that. So we get the circumcenter. Then we have the orthocenter. For the orthocenter H satisfies that H is equal to Z1 plus Z2 plus Z3 minus 2 times the circumcenter O, right? Which we got here before. So if you add up all the Z1, Z2, Z3 and subtract 2 multiplied by the orthocenter, which is clearly the circumcenter, which is clearly a complex number also, then you get this result right here. Okay, so add all the z1, z2, z3, and then you say minus 2 times O, and then you get auto center H to be 2.900 for the 2.91 for the real part, and then plus 2.27 for the imaginary part. So 2.9 comma 2.2 2.91 comma 2.27, or if you like 2.90 plus 2.27 j, like that. Then we have the Euler line. The Euler line, the centroid, circumcenter, and orthocenter lie on a line. So the line on which they lie is called the Euler line. So the centroid G, the circumcenter O, and orthocenter H lie on a line. They satisfy that H, that is this orthocenter, is equal to 3 times the centroid minus 2 times the minus 2 times the circumcenter. So you can verify the Euler line here. So if not, so in case anyone is not really here, this is what this condition is for. Euler line check is 3g minus 2o. Then print 3g minus 2o. That's the Euler line check. So print f of h to be h. Check if they are approximately equal to floating point arithmetic. So, all this code is for us to get 3g minus 2. We have 2.90 plus 2.27. So you see that Euler line seems to coincide with the ortho center in this case. Then the ortho center H also is 2.90, exactly the same as the Euler line. So H, G, and O are collinear, because if they are collinear, it means that they are basically functionally the same, or one is a multiple of the other. Okay, so the visualization now. So I mean, all this plenty code is to help us visualize. So, but this is what the code ends up giving us right here. So if you are interested in the code, you want to check it out later. Okay, I had not run the because all the parts are connected. So I'd run this too. Then I need to run this. It's not wasting time. So then I can run this now, and then that will this one can now work. Yeah, finally. So, yeah. So imagine you have your triangle this way. You have this triangle. So the blue line talks about are the triangle sides. So point Z, that's point Z1. Green, Z2. Is it magenta also? That's Z3. And then the centroid is somewhere here. The second center is somewhere here. And the ortho center is somewhere here. And then, so all of them lie on the Euler line. So, and this is the real part, and this is the imaginary part for all the points. So that's the representation of all of that. Now we can talk about the rotation trick. So for the rotation trick, right, you want to construct an equilateral triangle Z3, which is equal to Z1 plus Z2 minus Z1, e raised power plus or minus I pi over 3. So you import so we import CMAT. Let's say Z1 is 0 and Z2 is 1. So it means Z3 is equal to Z1 plus Z2 minus Z1 multiplied by the exponent of I, complex number, or J now, pi over 3. So in that case, now you run this. So you automatically, so with if Z1 is 0 and Z2 is 1, then Z3 is automatically 0.5 plus 0.86. That will give you an equilateral triangle like that. So if you plot all these points, 0, 1, 0.5, 0.86, you get an equilateral triangle. Of course, maybe, yeah. So, this one now is like 0, no, okay. Let me try to even pull it off on Desmos. Have I been able to do that before? Hmm, okay. I'm trying to think about this. Maybe I shouldn't bother. Let me just go on. Let me just go on. So I didn't just waste time. So, but we can just do it like coordinate system. This is for Z1, this is 0, 0, 0. That's the origin. Z2, that's 1, 0. The imaginary part is non-existent. And then we have 0.5, 0.87, if you like. So we can plot that on a coordinate system and you get an equilateral triangle. Then we have important identities like this. So centroid at origin. At the origin, the centroid is Z1 plus Z2 plus Z3 equals 0. Perpendicular lines condition, that's Z1 minus Z2 over Z3 minus Z4. And it belongs to imaginary real number. It's like IR. So it's imaginary in short. For collinear yeah, for collinearity, the case was real, right? But this one is IR like this. So you have an example here. Given z is I plus 1, z2 is 4, 1 plus I rather, and z2 is 4, z3 is 2 plus 3i. The centroid will be z1 plus z2 plus z3 over 3. Add it all up, you have 7 plus 4i over 3, like that. So in summary, we see that when we talk about distance, we are talking about the absolute value of z1 minus z2. The midpoint is z1 plus z2 all over 2. The centroid is z1 plus z2 plus z3 all over 3. The area, which we actually did a practical, we took an actual example, that's half of the absolute value of the imaginary of the product of z2 minus z1 and the conjugate of z3 minus z1. So the rotation is ZEI raised power theta. Then Euler line is H equals 3G minus 2O, like we saw practically. So again, we have 20 questions to chew. So look at this first 10 here and then look at the next 10. You want to try your hands on all of them. So of this 20, I'm going to answer two like I always like to do. I'm answering question one. So question one, given that Z1 is 1 plus I, Z2 is 3 plus I, Z3 is 2 plus 3, I compute the area of triangle ABC. Okay, it's like what I did the other time. Then, or should I choose another question? Okay, this one is asking for collinearity. This is 2 plus I. This is also 2 into 2 plus I. This is 3 into 3. So they are based, even without doing anything, by just saying that if you can factor all the other parts to get one of them, they are collinear. You don't even have to go the extra mile, you know. Okay, since I've done triangle before, maybe I should just focus on the other one, question 16, which is also very simple. Okay, maybe I'll just do uh, okay, I said I was going to prove something before, which I didn't do. So now I think I'm going to do okay, even question 16 is straight to the point. What do I do? What do I do? What do I do? Okay, maybe I should do question. Okay, I'll do what I was supposed to do in the other video to prove that absolute value of Z1 minus Z2 is the same thing as absolute value of Z2 minus Z1. And then I'll do this 16. And then I'll also show that the rotation preserves distance like this. So let me take them one after the other. Let me start with the simplest one. Since we've just done area here, I think it's okay. I should just go ahead. So first, I want to prove I should have done this in the last video. We want to prove that the absolute value of Z1 minus Z2 is equal to the absolute value of Z2 minus Z1. Of course, the proof is easy. We know this is absolute value of Z1 minus Z2, and that is the same thing as, you know, um, you can say this is the same thing as minus Z2 plus Z1, right? Nothing has changed. I just put minus Z2 forward and put Z1 back. But if this is going to be the case, we can then say this is the same thing. We can factorize minus 1. So we have minus into Z2 minus Z1. Make sense? This is minus Z2 plus Z1. Still, nothing has changed. Absolute. So then, since we are taking absolute value of everything, we can as well just move the minus out. So that means we have absolute value of Z2 minus Z1. So, I mean, it's a very straightforward proof like that because absolute means the minus doesn't matter. So at the end of the day, we can say so absolute value of Z1 minus Z2 is equal to absolute value of Z2 minus Z1. Easy peasy. So so the next question is this that's question 16 in this new case now. This question 16 here. So we want to verify that the absolute value of Z 1 minus Z2 all over absolute value of Z1. Absolute value of everything is equal to 1. Implies triangle is isosceles. Okay. And so isosceles means that two of the sides are equal. So if you can prove that two sides are equal, then we are good. So given that absolute value of Z1 minus Z2 all over Z1 minus Z3 is equal to 1, all right, what do we do? So if we take the moduli, okay, taking, we take modulus of each one, take modulus. So that means we have absolute value of Z1 minus Z2 all over absolute value of Z1 minus Z3 equals 1. Okay, if you like 1 over 1, we can cross multiply. That means absolute value of Z1 minus Z2 is equal to absolute value of Z1 minus Z3. And that's a very simple thing. So it simply says, so Z1 minus Z2 is the same thing as Z1 minus Z3. So that means equivalent. So the interpretation here is that, uh, so, so this implies that distance from Z1 to Z2 equals distance from Z1 to Z3, like that. So we can say hence two sides of the triangle are equal. So in conclusion, right? In conclusion, we can then say that triangle is isosceles. Triangle is isosceles. So, and it is based on the fact that with vertex as Z1, with vertex as Z1. Vertex as Z1 meaning that the distance from Z1 to Z2 is the same thing as distance from Z1 to Z3. So Z1 is like the reference point, basically. So the last one I like to do is question 19 now. Question 19, that find a complex number, oh no, not that, question 18. Show that rotation preserves distance, that absolute value of ZE I theta is the same thing as absolute value of Z. Okay, so to show to show to show that rotation preserves distance, okay, that is the absolute value of ZE raised power I theta is equal to absolute value of Z. What do? We have absolute value of ZE raised power I theta. That's the same thing as absolute value of Z into into of course, since, let's do it this way, since Z is equal to X plus IY and e raised power I theta is equal to cos theta plus I sine theta, okay, this is one way to do it, right? Then we can say that the absolute value of ZE, hope I'm doing the right thing. Let me check again. ZE raised power I theta, right? I believe that's it. ZE raised power I theta, correct. So ZE raised power I theta is equal to absolute value of X plus IY into e raised power I theta, that's cos theta plus I sine theta, like this. So that means we can expand. Now, if you expand X times cos theta, that's X cos theta. X times I sine theta, that's IX sine theta on one hand. Then IY cos theta, that's IY cos theta on the other hand. Then IY plus I sine theta. So that's, okay. I times I is I squared. Okay, where I can say I squared, right? I squared um, Y sine theta. Okay, I squared I y sine theta. That's IY times I sine theta. That's I squared y sine theta. So that means we have X cos theta plus IX sine theta plus IY cos theta. I squared is minus 1. That's minus Y sine theta, like this. So if you put the same together, it means we have absolute value of x cos theta minus y sine theta plus I is common here, so I into x sine theta plus y cos theta. And then if we do what this actually means, so this simply means square root of, okay, everything together, in fact, that's square root of x cos theta minus y sine theta all squared plus x cos theta, rather x sine theta plus y cos theta all squared, right? X cos theta minus y sine theta squared plus x sine theta plus y cos theta squared. So we can expand all of this now. So if you expand this, this is like x squared cos squared theta minus 2xy sine theta cos theta plus y squared sine squared theta. This is just for this alone now. I think I need to expand this down. Then all this now plus x sine theta plus y sine y cos theta all squared. That's x squared sine theta, sine squared theta, then plus 2xy sine theta cos theta, then y squared cos squared theta, that's y squared cos squared theta. Okay, so with this now, this cancels this straight up, and then we have square root of x squared cos squared theta plus y squared sine squared theta plus x squared sine squared theta plus y squared cos squared theta. So we can collect like terms now. I think that will be in terms of whether it's okay, like all this now. You have x squared cos squared theta, x squared sine squared theta. So we have square root. X squared is common, so you have cos squared theta plus sine squared theta, like this, plus y squared is common here also, so you have y squared into sine squared theta plus cos squared theta, like this. So then we have all of this to be square root of x squared. Cos squared theta plus sine squared theta is 1, clearly. Then y squared, that's sine squared theta plus cos squared theta, is also 1, right? So we have square root of x squared plus y squared. Uh, therefore, the absolute value of z e raised by I theta is equal to square root of x squared plus y squared. Okay. For absolute value of z, right? We know that's absolute value of x plus iy, and that simply means absolute square root of x squared plus y squared easily, that's the modulus. So overall, absolute value of z is equal to absolute value of z e raised by I theta equals absolute square root of x squared plus y squared. The only thing is that the other one took a long time to arrive at, but it's the same thing in essence. So with this, I'm done solving all that. So don't forget to try your hands on the questions, the 20 of them. This is 1 to 10, and this is 11 to 20. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for that. If you have not subscribed, what are you waiting for? Go ahead, subscribe, and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges like getting to some videos first or seeing some videos exclusively, right? Um, then another thing you can request for PDF copies of the notes I'm using for these classes, or we can hang out together virtually or physically if you're in the same geographical location, talk about anything that interests you on my channel. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.